So the second exercise on the embed operating system and the classes and how to use those classes, define the object in our own code is how to control an electric motor. So I have another board in here, and in this one, I have two of really small electric motors in here. So there is a motor, and then a gear, and there is an axle which is rotating according to my control signals. And the microcontroller output, the pins we were using to drive the LEDs in here in the earlier exercise, these output pins can drive the current up to 20 milliampere each. And then you can just drive like an LED indicator light, like in here. But it's not capable of driving a motor like we will need in here in this circuit. And for this reason, on the output circuit, we are using field effect transistors. So there are transistors in this circuit. So these are the transistors, transistor 1 and transistor 2, driving the motor 1 and motor 2. And to give the setting for the speed, I have the same way, the potentiometer in here, like in the earlier example. So I'll connect that one, but we will first have a look on the code. And then what we need to do is explained in the document in here. So it is the picture of exactly the same board that I have in here. And then there is the small electric motor with a gear in here. And then, anyway, there are a number of different types of motors that we sometimes need to drive with this small microcontroller. So there are brushed DC motors. So this is in Finnish the tasasähkömoottori, harjallinen. So this is the traditional direct current motor. So that can be found in toys nowadays, low-cost toys and low-cost power tools like cordless drills and so on. And then there are AC induction motors. So these are motors used typically in the industry. So in Finnish, it would be oikosulkumoottori or vaihtosähkömoottori. So it's an alternating current motor. So it's typically driving with the three-phase alternating voltage in industry. So 400 volts, three-phase circuit, and the power is some kilowatts to some hundreds of kilowatts. So rather big motors. So sometimes we need to be drive those. And then the third one is a step motor or stepping motor. Both of the names are used. So it's an askelmoottori in Finnish. These are in applications like in a copying machine. And the reason to use those in a copying machine is that the paper drum is rotated and then kept in certain position. So when you need to keep a certain axle in a certain position and then rotate it a few steps forward and then keep it in the same exact position again and then rotate a few steps forwards, then you might use a step motor. It's not really driving anything like supplying the power for some movement or whatever, like a motor. It is more like you just rotate a certain axle for certain steps. Then there are brushless DC motors. So this is harjaton tasasähkömoottori. And this can be found in modern tools. So the reason for that is that the construction is simple, but you need some electronics to drive it. And then with that type of motor, you can drive the motor with very high speed, so rotational speed. So then you get a lightweight motor with a high power output when you can drive it with like 10,000 rounds per minute or something like this. Then there are permanent magnet AC motors, so alternating current motors, but with a permanent magnet. So in Finnish, kestomagneettimoottori, then vaihtosähkö. So it's alternating current, permanent magnet. And that's, for example, quite often in the electric voltage drive for the modern cars are, for example, using the permanent magnet AC motors quite often. And then there are synchronous AC motors, so tahtimoottori, vaihtosähkö. So that's another option when you drive an electric drive in a modern car. It is typically either permanent magnet AC motor or synchronous AC motor. So it's alternating current, although there is a battery which is delivering direct current. So akku, joka tuottaa tasasähköä, mutta moottori siellä on aina vaihtosähkömoottori ja usein tämmöinen kestomagneettimoottori tai tahtimoottori. So it's either the permanent magnet AC motor or synchronous AC motor to drive an electric motor or to drive the axles in a car, modern car. And then that's built from a factory that's from the BMW group. So from the year 2019, and there is someone like constructing the electric motor. And this is probably a typical AC motor, alternating current motor. So this is the starter. So this is not rotating, but the rotating part will be inside in here. And then, but nowadays the motors are constructed in a car quite often like this. So this is from a Mercedes-Benz, a hybrid model where there is some kind of electric motor in between the gearbox and the engine. So the motor is actually built there in the construction. So you can't like find an electric motor in the car because it's built on actually in the gearbox of the car inside there. So what are the motor drives then? So if we drive something in industry, we go to companies like the ABB and have a look at what is an ABB, what is an AC drive, and so on. And then the simple way of driving a motor is that you have a direct current motor. You have some kind of power supply with plus minus voltage. So this is the direct current. So because it's plus minus, not an alternating current. And then you just close the switch and you drive the motor. And the motor is, always when you look at the motor, there are the coils. So there is a coil of wire in here. Or there is a coil of wire in here. And that makes that it's an inductive load because it's a coil. And from the electrical point of view, the inductive load is such a load that when you try to switch off the current, the coil is trying to push the current still forward. So when you cut off the supply from here, the current continues to flow in the motor. And then it will draw this point, if you open it in here, into minus 100 voltage, minus 200 voltage, or minus 1000 voltage, until there is like a spark in between these points. And finally it's burning the contactor from here. And that's why there needs to be a freewheeling diode when you have a direct current motor. When you cut off the circuit, the motor is still pushing or the coil there is pushing the current this way. And then you need to have a diode here so that the current is circling here as a freewheeling after you open the circuit, a few hundred milliseconds. So the time of a few hundred milliseconds, it is circulating here, rotating here the current. So then when we put here a microcontroller, this is our microcontroller board. So as this is capable of driving only like 5 milliampere or 20 milliampere, it's not capable of driving a big conductor, so a relay where there is a magnetic, which is like closing and opening this contact. So this takes so much current to control the magnet in here, so or the switch in here, that you need a power circuit in here. So you need a relay driver integrated circuit in here to drive that conductor. And then the motor circuit is the same. You have the direct current supply, and then the opening contact, closing contact, and the motor and the freewheeling diode. This kind of control circuit, you can just open, close the switch, like you don't do it 100 times in a second, because that's a mechanical switch. So if you need to do it more frequent, then you put there a transistor on the circuit. So now I have a power MOSFET transistor in here in the circuit, and then I have the similar direct current motor, the power supply plus, the power supply minus. I supply the current through the motor. Goes, if I control this MOSFET to on state, the current flows through the MOSFET transistor back to the ground, back to the minus of the power supply. So the current is flowing in here. And then with this kind of MOSFETs, we can drive the current up to a few hundred amperes. And then it's the same problem. We need a freewheeling diode, because if we cut off the current in here, the motor is still pushing the current this way, or the coil here, because it's an inductive load, is pushing the current. And then if it just cut off the circuit from the MOSFET, this voltage goes to plus 100 volts, plus 200 volts, plus 1000 volts, and it's blowing the MOSFET. That's why we need a freewheeling diode in here. And then I have another power supply to supply the 3.3 volts to my microcontroller. So that's the 3.3 volts, and that's probably 200 volts or 48 volts or whatever the motor needs as a voltage. And then I have a power MOSFET in here as a switch. We are using this transistor as a switch. And then if I would like to control the speed of the motor, so this is a typical direct current motor. There is the coil visible in here, and then that's the axle, and that's the rotating part inside there. And that's the MOSFET transistor I'm using for controlling it. And then in principle, I'm supplying the motor with 12 volts. If I control the transistor that it is most of the time conductive, so that my control voltage, the gate to source voltage, the control voltage in here is 3 volts for most of the time. Also on the motor, there is 12 volts most of the time driving the motor. And then if I control the transistor so that it is controlled with the 3.3 volts, just 30% of the time, then it's off. Then 30% on, let's say 33% on, 67% off, 33% off, on, 67% off. So 1/3 of the time it is on. So 1/3 of the time the motor gets also the full 12 volts, and then 0 volts, and then full 12 volts, and so on. So the motor is actually driving like it would get 1/3 of this voltage. So it's driving like it would get 4 volts. So, and with the voltage, we define the speed of the motor. So this is the circuit that we drive the motor with different speeds when we cut off the on-off switch circuit, this transistor in here. We cut it on and off and on and off like 20,000 times in a second. So the frequency here for cutting the voltage, that frequency is 20 kilohertz. I'm using 20 kilohertz because it's outside the human ear audio signal hearing range. It's so high frequency that if it is making some noise on the circuit, then we won't hear it. If we put there a lower frequency, then we will hear some kind of annoying noise from the motor, because the motor is a little bit mechanically vibrating when we cut the circuit on and off. So if we cut with a very high frequency, we get almost no noise from the motor. And then, yeah, that's the way, let's say, always the direct current motors are controlled with the pulse width modulated signal. So this is the pulse width, which is defining the speed. And then that was defining the speed. And then we can also define the direction of the driving. So that I have one MOSFET transistor here working as a switch, another one in here working as a switch, and then also in here and in here. And when I put my MOSFET number 1 conductive and MOSFET number 4 conductive, I get the current flowing that way and through the motor from left to right. And my motor is rotating, let's say, clockwise direction with this current. And if I would like to drive it to the opposite direction, I put MOSFET number 2 conductive and MOSFET number 3 conductive. And then I got my current flowing in here through the motor in the opposite direction. And then the motor is rotating in the opposite direction. So that's the way of controlling with the microcontroller, the rotation direction of the motor. So I'm controlling all these MOSFETs, MOSFET number 1, MOSFET number 2, MOSFET number 3, MOSFET number 4. And then I can handle that which way the motor is driving. And then I can also, at the same time, give that pulse width modulated signal to these MOSFETs, and then I'm defining the direction and the speed. And then that could be done on the code of the microcontroller. But typically it's done in a motor driver circuit, so that you have a specific integrated circuit which is doing that, so that all the functions are inside some circuit, and then the microcontroller is just telling that circuit that what kind of speed it needs from the motor, and that circuit, integrated circuit, is then driving the motor. And then what we do with all this information is that we need to understand that how to drive the motor. And then how to drive the motor in our code. So we are using with the Embedded OS operating system, we go to the documentation and there into the PwmOut. So we go into the documentation, the Embedded OS, and we go into the API reference and tutorials, and we go into the PwmOut, pulse width modulated signal output. And here is my class definition, and then the methods in this class in here. And that would be then creating those signals that we would need for driving in motor with different speeds. So that PwmOut is producing this pulse width modulated signal.